Can you see my screen? Yes, no, please. Can you see my screen?
Yes, sir.
Yes, sir.
Okay, thank you. So let me just see. Okay, so we have looked at so far on basic routing functionalities of IP. How is the routing table built? How is it used for forwarding? How is the networks are represented, and so on. Now we look at the other side functionality of IP called fragmentation and reassembly. So network layer has, for IP in network layer, has two basic functionalities: routing and fragmentation and reassembly. We have covered routing, so we'll go look at fragmentation and reassembly. So the idea is simply this. So for every network below, there is something called a maximum transfer unit, which is the maximum size of a physical frame. As we have seen, for Ethernet, it's 1518 bytes, including header, to 1500 bytes for the data. So typically, when we talk about the MTU at the network layer, we talk about basically the part without the header. So we'll typically say the MTU for the network being used is 1500 bytes. Okay. So think of a router, okay, and it has all these outgoing links. And it has got a packet which is some, let's say, 2000 bytes of data, IP packet. So the data part is 2000 bytes. But then this link has 1500 bytes maximum at the data link layer itself. Okay, think of that as an Ethernet link. So now I cannot give the 2000 byte to this Ethernet layer because the Ethernet cannot transmit more than 1500 bytes. So Ethernet will simply discard the frame. Okay, so you don't want to do that. So what you will do is, but you still want to transmit the 2000 bytes as a single unit. Okay, so well, not as a single unit, a single logical unit. We'll see what happens. Physically, you cannot. So you fragment. Okay. So this is what is called fragmentation. When a router transmits a packet that is too large for the MTU of the outgoing link. The MTU of the outgoing link is 1500 bytes at the data link layer, but you want to transmit a packet that is 2000 bytes. Okay. Then the router will first fragment the packet and then segment. And I'll show you examples. Fragment may also be fragmented later on, but we'll talk about this later. And then these fragmented packets will not be reassembled until they reach the final destination. Okay, so think of a simple example. Forget about a router. Think about your source machine. Okay, this is your source machine, and the TCP layer here, the IP layer is here. Your TCP layer gives you 2000 bytes, and you have an Ethernet link here. Okay, so I know Ethernet is maximum 1500 bytes. Okay. So what this will do is to break up this 2000 bytes into two fragments. Okay. And we'll see what the sizes will be. Just for now, just suppose 1500 bytes and 500 bytes. And then they will be transmitted as separate frames, separate IP packets all together. And then, so now my original IP datagram of 2000 bytes is actually being transmitted as two IP packets, one with 1500 bytes of data, one with 500 bytes of data. Now, when will I put them together and give the 2000 bytes to TCP? Okay? Because at the other end TCP, the destination end, TCP does not, there is an IP layer, and this has to give 2000 bytes. Okay? So all these fragments will come here and wait at the IP layer. And then when all the fragments come, we'll see where information within the fragments to kind of see which order they should be put in and so on. They will be reassembled and then they will be given to the higher layer. So the reassembly will only happen at the destination. There will be no reassembly in the middle just because now I encounter a router and that can transmit 3000 bytes, but that doesn't mean that I will reassemble them. Okay. So fragmented packets are not reassembled until they reach their final destination. And then typically, we look at this again. If any fragment is lost, so suppose I break this into 1500 and 500, I transmit them as 2 IP packets. And then at the destination is waiting. It has got the 1500 bytes, but does not get the 500 bytes because IP is unreliable. So maybe some router drops it, whatever. So what will happen to this 1500? Okay. So the router will simply wait for some time. Okay. It's not the router. This will be the destination. Okay. The destination will simply wait for some time for that 500 bytes to come. If it does not come within some time, discard the 1500 also. Okay. Because the higher layer, it will only give after reassembly. So if it cannot reassemble within a reasonable time, because packets are some fragments are delayed, some fragments are lost, and so on, we'll just discard the packet. Enter. So you understand fragmentation is not good. You don't want fragmentation to happen. Okay? But sometimes we don't have any option. So this is a typical time, just to give you an idea. In the standard IP implementations, typically you wait for all fragments of a fragmented packet to come within 30-60 seconds. If they don't come, you discard everything that you've got so far about that packet. Okay. We'll look at an example very shortly. But first, in the context of fragmentation, we want to distinguish between these 2000 bytes and these 1500, 500 bytes. So IP datagram is the unit we talk about, is the unit of end-to-end transmission before fragmentation and after reassembly. Excuse me. So that is the 2000 bytes. Okay. And a packet is what you have seen, something on which I put an IP header and send it. So packet is a unit of data actually passed between the IP layer and the data link layer, and which then gets routed individually. So these are 1500 bytes, 500 bytes that I'm talking about. Okay. So packet can be a complete IP datagram. Suppose you are sending only 800 bytes of data in a datagram. Of course, it can go as a single packet, or it can be a fragment of a datagram. Okay. So sometimes people, normally we will not just talk about IP packet, but in the context of fragmentation, because we have the entire data that is supposed the IP wants to send, and then because the MTU restricts it, it has to break it up into smaller things, which will be routed independently. Okay. So we distinguish between these two terms, datagram and packet. Now, how do I know? I said that I will wait for all fragments to come, etc. How do I break it up? How do I decide how much to the 1500, 500 or something? Okay. How do I know all fragments have come, etc., etc.? So the three fields in the IP header that we have not looked earlier. So this is nothing. This is just in the middle of the IP header. All the other fields of the IP header are there. When we have shown you the IP header, you have seen this field, identification offset flags. Okay, but we did not discuss it there. So I will have a packet identification. So each datagram will have an unique ID. Okay. And that's the idea I will put in here. And this I'm talking about. Okay. Fragmentation offset, we'll see what it is. It's kind of going to say what is the position. Okay. So I said 1500, 500. Okay. So this 500 thing that is being sent now. Sorry. Okay. So this is 0. Then somewhere there is 1500, 1. Then there is something. Okay. So this will kind of put it here, saying that the data that I'm carrying is actually from the 1501th offset of this, actually 1500 because it starts from 0. Okay. So 0 to 1499 is carried in the first one. Okay. And then 1500 to 1499, 1999 is carried in the second one. Okay. So I will put this offset. What is the starting position of the first byte that is being carried in this pocket in the entire data stream, the datagram thing that we are trying to do. Okay? And we look at examples. And then there is reserved flag. Don't worry, it's not used for fragmentation, but there is these two flags, don't fragment and more fragments. We'll see what it is. So here's a quick description of the thing. Fragments are identified using the datagram identification. So when I break a datagram, every datagram has a unique ID. In all fragments of the datagram, I'll put that same unique ID to say all these fragments belong to the same datagram. Okay. So that's how I first of all I identify that these 5 packets that have come, they're actually part of the same datagram because they have the same identification. Okay. And then the sequencing I will do using the fragment offset. So as I said, the fragment offset contains the offset from beginning of data carried by this fragment. But then I will not do that 1499 and this will be in units of 8 bytes. So all fragments except the last, okay, must carry a data which is multiples of 8 bytes. So I won't break it in 1500 and 500. I'll actually break it into 1496, which is the next lower thing divisible by 8 below 1500, and then the remaining part is rather 504 in that. Okay. I'll look at an example shortly. And then the more fragment bit will decide. So how do I know? See, think of that you are the destination. Just try to visualize with me. Okay. And you get one packet. Okay, with something in the identification field. How do I know it's a full data or it is something else basically? Okay. So this more fragment bit will tell me partially that. I'll set that more fragment to 1 if there are more fragments to follow with it. That means if I break up a datagram into 4 fragments, just suppose the first 3 will have more fragments bit set to 1, indicating there is another fragment of the same datagram after this. The last one will have the more fragment bit set to 0, indicating no more fragments after that. Okay. Are you with me? But then, how do I determine? Just think. Okay, we'll come to this. Let's look at the example, then we'll come to this question. So let's look at an example. I want to send an IP datagram of size 2000 bytes without header. Okay. With identification field 1, 2, 3, 4, 5. All right. This part I will check because the IP header will be carried within this thing also. So I'll check this. Okay, just for now. Okay. So the MTU is 1500 bytes without header. That means in the Ethernet, just suppose the Ethernet network. Okay. So you have a frame. This data part, okay, must be maximum 1500 bytes. That's why I will check this because IP header plus this should fit into this 1500 bytes. Okay. So now I'm going to break it up into 2 things, 1496 and 504 bytes. Okay. So these 2 fragments of 1496 and 50 bytes, 1496 because as I said it has to be a multiple of 8 bytes. So your fragmentation 1 will have the identification 1, 2, 3, 4, 5. Just suppose the datagram identification field was that unique ID was 1, 2, 3, 4, 5. Its offset will be 0 because it's carrying data from byte 0 in this 0 to 1999 bytes. So 2000 bytes mean my offsets are 0 to 1999, the last one. Okay. Fragment 2 will have the same identification field. Offset will be 187. So 187 into 8 is actually 1496. Okay. So this is basically saying in this string, the second one is carrying data from offset 1496 to 1999. 0 to 1495 is carried in the first fragment. And the more fragment for the first one will be set to 1. More fragment for the second one will be set to 0. And these are just like normal IP packet. So rest of the field will be exactly the same, except of course the checksum will be different because the header checksum will depend on the header fields and the header field of these two header fields are different. So checksum will be different. But all other fields, TTL, sequence number, etc., window, etc., that you have done, not window, sorry. Everything that you have done, that, sorry, not sequence number, length and everything, H lane, everything will be the same. Okay. And then these two fragments will go as independent IP packets. They will reach the other end. And then the other end will basically see that suppose it gets this one first, this fragment one first. Okay. So it sees the identification, it sees an MF equal to 1. Okay. So it knows there is something has to come. So you don't deliver it to the TCP layer, you'll just buffer it. Then later on, if this comes, okay, you'll see 0, 187, that means it knows how much data is here. So it will just piece together these two data because now the MF field is 0. Okay. And you see there is no missing thing because I have offset 0, offset 187, which is 1496 basically. Okay. And at the data field length from the first header. So I know this had 1495 bytes. This is the offset. I know this one has this. More fragment is 0. So I will piece these two together as a single datagram, give it up to the TCP layer or UDP layer, whatever. Are you with me? Yes, no, please.
Yes, sir.
Okay. And for some reason, if this comes, but then this does not come within a certain time, I will just drop this. So when this comes, this will again have to wait for some time because I don't keep any history, and then this will get dropped because this is not going to come. Unless there is a reliable protocol above and so on, don't worry about that. No action. But that we have not come to the transport layer yet. Network layer does not do any error control or anything. Okay. What happens if this comes first? Before this, now my MF field is 0. Okay. How do I know that it is a fragment of a datagram or it is a full datagram? Should I just by looking at the MF field, I cannot decide that, right? Just think of a normal datagram which is not fragmented. I said 800 bytes in some datagram. So that datagram is not fragmented. So more fragment bit will be set to 0 for that anyway, because there is no fragment. The entire datagram is one packet. Okay. So the question is, when I get this one, how do I look at my MF field is 0? That will be 0 for a normal datagram also, which is not fragmented. So how do I determine, looking at this fragment that has come, that is just the IP packet that has come, okay, that is a fragment of a datagram and not an actual datagram. And therefore I should buffer it and not give it up to the higher layers. How will I determine that? Come on, this is simple.
Offset is non-zero.
Exactly. Okay. So in a normal datagram that is normally not fragmented, offset equal to 0 always. So even if the MF flag does not help me, the offset flag helps. Okay. So I can always reassemble irrespective of the order in which it comes. So I told you basically the reassembly thing. Okay. Now this fragment can get fragmented again at an intermediate router. Okay. So I fragmented at the source because I had an Ethernet link going out. So at this 1496 and 504. Okay. At router in the next link MTUs, for example, somewhere in the middle, okay, this come all the way out here. This next link MTU is 900. So fragment 2 was of size 504, that will pass through fine. But fragment 1, okay, which is 1500 bytes, sorry, 1496 bytes, this cannot pass through. So what this router will do, okay, is to break this up again into two things. Okay, again it will break into 896 and 600, 896 because the lowest multiple of 8 below 900. Okay, and then the remaining part. So fragment 1 now has two fragments, 1A and 1B. I will always put the same identification everywhere. But now just think about this as a packet and decide the offsets out there. So first offset will be whatever the offset that was being carried there. Next offset will be that plus whatever this 896 by 8 is. In this case, that is 1 0. So first one had 0. This will be offset. So this won't be 0 always. If fragment 2 was fragmented, this one would have been the offset that was carried originally in fragment 2. This one will be that plus whatever the size of this fragment divided by 8. Okay. And MF bit I will just copy. Am I correct? Should I just copy the MF bit? For fragment 1 I will copy. Okay, because I know MF bit 1 means there is one more fragment, which is at least one more fragment which is coming after this. Okay. So in this case, it's safe to copy MF bit. If the MF bit was 0, then what would I have done? Anyone? Suppose I'm making a fragment which is the last fragment. So MF bit is 0. Anyone? See, just use your common sense. Okay. Finally, exactly one fragment arriving at the destination can have MF bit equal to 0. Two fragments cannot have MF bit equal to 0. The destination does not care where it is fragmented, whether fragments are fragmented and all these things. It's just getting a sequence of IP packets with the same identification field. Okay. Exactly one packet with offset 0 and then the offsets matching accordingly. And exactly one packet with MF equal to 0. So if I fragment a packet with already MF equal to 0 into maybe 2, 3, whatever fragments, I'll put MF equal to 1 for all the sub fragments except the last one for which I will put MF equal to 0. So that's what it's supposed to be. Are you with me?
Yes, sir.
Okay. This is very simple, very common sense. Okay. So if you just take instead of 900, you take 400, then that 1496 will break into multiple frames, multiple IP packets, sorry, 4 of them, and then this 504 will break into 2 of them. You should work it out yourself. You just put the exact fields and so on. These are very standard exam questions also. Okay. Whether you understood the basics, I will never ask you to describe what is fragmentation and reassembly. I'll probably give you a small problem to work out, fill up the fields and so on. So I know that you will understand. And then some small quiz out of that. Okay, so that is what is fragmentation outside. What if we do not want a packet to be further fragmented? Okay, you can set that DF flag. Okay, so if a router finds that it cannot transmit because the MTU of an outgoing link is smaller, but then the DF flag is set, it will just drop the packet. Now, why is it? Will never we want to use it? We'll see, discuss a scenario later on. Okay, but this is not commonly used. So DF will mostly will be set to 0. But DF, if you set to 1, it tells that do not fragment this fragment any further. Fragment datagram, whatever, that IP packet any further. Okay, so that is simple fragmentation and reassembly. It's a side, small, easy to understand thing. You just need to work out an example to understand what is happening basically. Okay.
Excuse me, sir. I have a small doubt.
Yes, sure.
Sir, in the previous slide, if we get the fragments in the order 1A and then 2 and then 1B.
Right. So you see what will happen. Good. Let me go through this. Okay. You got 1A. So you got offset equal to 0, MF equal to 1. Okay. And then there is this header field out there. If you recall the header field, you can have the amount of data in there. Okay, that will change now. Okay, so you know exactly how much data this is carrying. All right. Now you got 2. So 2's offset is 1496.
Yeah.
Okay. So you got something with offset 0, MF equal to 1, so there are more fragments, and with a size of 896 bytes. The size is, remember, is there in the header field.
Yeah.
Okay. And then the next one which has come says the offset is 1496, which means 1495 bytes are supposed to come there. But you have got only 896. So you know there is a gap.
Yeah.
So you're going to buffer both of them.
Okay, thank you.
Until the 1B comes. And if 1B does not come within a time, you will drop both of them. And if 1B comes later because it got delayed or something, that will get dropped also.
Okay, thank you.
Okay. So next what we do is a simple protocol called ICMP. You've heard about it. It's called Internet Control Message Protocol. It's important because we use it and it's a required protocol for any IP implementation. So you cannot say I have implemented IP if you do not have an implementation of ICMP. It's a required protocol for ICMP with IP. So any network stack that you will have with TCP stack will have ICMP in there. Okay? And is used for reporting errors back to the source of an IP packet. For whatever uses, I'll show you some uses. So basically, I would not say detects an error. Be more specific, drops an IP packet. So as we know, IP is an unreliable protocol, so IP packets can be dropped in many cases. So when an IP packet gets dropped, okay, the machine which drops it, the router, whatever, okay, the destination machine, whatever, drops it, it's going to send back an ICMP packet of appropriate type. It's only error reporting, there is no error correction, no error trace, okay. So correction is left up to the source node. If you are using TCP, TCP will time out and resend and all those things will happen. And here are some initial RFC numbers if you care to look. Okay. Now, how do I transmit back? Okay. So one IP packet was going, came to the router, it got dropped there. Okay, not further transmit, whatever it is. This will send back an ICMP. Okay. What it will do is, so an ICMP packet will have an ICMP header, okay, and ICMP data, and this entire thing will be just encapsulated in an IP header. You have to start visualizing these things a little bit now. Okay. So router drops an IP packet, it creates an ICMP packet with its own header, own data part, and so on. Okay. And then transmits that ICMP packet, the entire header plus data of ICMP, as data in an IP packet. It knows what the destination of that IP is, because if I dropped an IP packet, okay, I have the source IP filled in there. So when I transmit in the reverse direction, this source IP of the packet that I dropped becomes the destination IP. And the source IP becomes whichever machine, the router or whatever, dropped it. And then I can calculate all these other fields out there. There is no fragmentation here. So all of these will be 0, etc., etc., etc. Okay. So an ICMP packet is sent back just as a normal IP packet. The only difference is now when this ICMP is going back as an IP packet, that can also be dropped. But then if an IP packet that is carrying ICMP is dropped, then no ICMP is sent. Because then I will go into recursion. I again send an ICMP, that gets dropped, another ICMP, and so on. So we don't want to increase the traffic too much. Now, how will I know whether an IP packet is carrying ICMP packet or not? Anyone? Anyone recalls the IP header at all? Okay, go back and check the IP header. Similar to Ethernet, there is a protocol field out there which says which protocol's data is this IP header carrying. So when an IP packet is supposed to be dropped, the IP software will look at that protocol field. If it is anything but ICMP, it will send back an ICMP packet. If it is ICMP, it will do nothing, just drop the packet. Okay. The other observation is that this is more a philosophical thing. that ICMP is carried in IP packet. Okay, TCP will also be carried in IP packet. UDP will also be carried in packet. So in a sense, ICMP is above IP, okay? But we do not consider it like a transport layer. It's a required support protocol at the network layer on, even though it's actually carried with an IP packet, just like TCP UDP. Same goes for these routing protocols, as I said. OSPF, for example, is carried as UDP, so it's sort of above UDP layer. But then we do not really consider this as an application protocol. So sometimes these layerings, who is doing what in which layer gets a little blurred. Okay, but mostly it is. And we'll look at the ICA. We don't expect you to remember this, okay? But this nice thing to look at. Basically, you will have a type field, code field, and a 16-bit checksum. So checksum is for error detection. So nothing special. And some of these things are interesting. So these are the different types of things. So what basically type and code field says, the IP, the router which drops the IP packet will fill up this type and code field. So that when it reaches the source, okay, of the packet, you get an indication why it was dropped. But then everything is not for drop. So this echo request and echo reply are basically something that is not for drop, it's for monitoring. Okay. So we'll look at this issue of this echo reply, this all this. Let's look at this. So echo request reply is something. So it's the basis of the actually what is happening is that you are sending an ICMP echo request packet to the destination. Okay. And then when the destination receives the ICMP layer there receives the packet, it is by rule, it is supposed to reply to the ICMP reply packet. So you start a timer, you send an ICMP echo request packet, and then the reply comes back. Okay, you send actually multiple IP echo request packets. And the reply comes back, and you measure the time. That's the round trip time that you see when you do the ping. Okay. And then you have an identifier sequence number in this rest of the ICMP header part. This kind of a dead part, okay, which basically says that you have to match it because you send 4 ICMP echo requests and the reply came, okay, and you want to do the round trip time. You need to know which one's reply. Is the first one's reply or the fourth one's reply? Because IP, as I know, is unreliable. The other ones may have been lost in the beginning, okay, and it doesn't guarantee in order also. So even though the destination may have reached all 4 in order, replied to all 4 in order, the fourth one may come earlier than the first one. So you just need an identifier to say, oh, this reply was for that request. So that request I sent at 11:01, this come at 11:02, so that the time difference is wrong. Okay. And then there is an optional data part and so on. Why? I'll talk about a very interesting application later on if you want. Okay, but let's first finish the syllabus. But this is the basic of ping tool. So this is one example. So even though we routinely say ICMP is something that is sent when an IP packet is dropped by a router, this is something example where it is not a drop. Okay, it's something that is given to you to monitor whether a destination is up or not. And then destination unreachable is when a router cannot forward or deliver a packet. Okay, again, you don't have to remember all these things. You don't have to remember. Remember, there is a type, there is a code. That will be there in everything. So this first 3 fields will be everything. What will be here will depend on this type and the code. Okay, but you don't need to remember any of these packets. All right. So, but then destination unreachable can be for many things. It can be because there is no entry in the routing table. Okay, it can be because if the network is there, but when I send an ARP request, okay, nobody replied, so the host is not there. It may be because the IP header has a protocol field that is not recognized. Okay, it may be because the port is not recognized. Okay. Now this is where if you think with me a little bit, the layering breaks down a little bit. IP header is not supposed to look at port. Okay, it's got an IP packet. It's not supposed to look at ports. Okay. But then we'll see that layer index now, the TCP will tell the port is not reachable, something will happen. Okay. So that's one of the example, fragmentation needed in DF set. Okay. And then there are other reasons out there. So just remember that the packet may get dropped at the router for many reasons because the destination, but destination, what is destination? It may be no entry in the routing table, which means even the network is not there because routing is by network in the routing table. It may be something matched, some network matched. I know it is in this network. But then when I sent an ARP request, okay, nothing came back because you specified, you were supposed to specify 10.125, 20.10.0, sorry, 5. Okay, this is my network part, and you specify 120.10.7 by mistake, and there is no machine with IP 10.120.10.7. So the network part will match in the routing table, but when I try to find out the MAC ID of 10.120.10.7 by using ARP, nobody will respond because the machine is not there. Nobody has the right. So that will be your host unreachable case. Okay, the protocol unreachable case for whatever error you specify a protocol that is not there at all. Again, you don't have to remember the details of each and every one of them, but let me say these two are easy to understand. Okay. This one, just read. Okay, it's sent when a packet is dropped due to buffer overflow. Okay, so sort of reporting a congestion at an intermediate router. Okay. So I'm going through this type code field just to give an example of the kind of things that the different types of things why packets can get dropped. But you should actually try to remember kind of, as I said, just think about the packet's flow, okay, and just think about everything, at every step what can happen. How is it forwarded? How is it done? Okay, and then what if this is not there? Then what will happen, and so on and so forth. Route redirect is something I'll skip. Okay, it's a little bit odd, hardly ever used. Then this time exceeded for datagram. TTL equal to 0. Okay, when the TTL becomes 0, remember that every router, when it transfers the packet, IP packet, will reduce the TTL by 1. And the TTL becomes 0, it will get dropped. How many of you know the trace route tool? Anyone knows the trace route tool? Trace route, trace RT. Yes, no? So the trace route tool, as the name suggests, okay, traces a route. So if you say trace route, give an IP address or some DNS name also, it'll show you the route to that thing. Okay, it'll show you all the intermediate IP addresses, router IP addresses. Okay, sometimes we block it here inside IIT Kharagpur and all, but you can try it from outside and so. Okay. So how do I get? Okay, what are the intermediate routers out there? Can anybody think? So can I use this time exceeded thing, feature of ICMP, to find out, let's say, all the routers from me to some abc.com, all the routers that my packet will go through. It's not a foolproof method. It works most of the time. Anybody wants to guess? Okay. It's very simple. Okay. So I understand it will be hard to come by all of a sudden if I ask. I'll do this. Try to follow me here. Okay. Here is the source. Okay. Here is my abc.com. Okay. And there are lots of routers, but I don't know them. I do not know how many. I do not know what the things are. Okay. So I'll first send a packet for abc.com. Okay, just an IC, simple IP packet. I'll create an IP packet, source IP this, destination IP destination of this, which I can get by DNS. Okay, with TTL equal to 1. So what will happen? The first router will drop it. Okay. When it drops it, it will send you an ICMP packet with the type field set to time exceeded and the code field set to 0, which is the code for TTL equal to 0, because you can have time exceeded for two reasons: TTL equal to 0 or that fragmentation reassembly. If it was fragmented and all the fragments did not arrive within certain time, then the datagram. Anytime a datagram is dropped, it will send it ICMP. Okay, but let's code with this. So it will send the type, whatever the type for this code 0. All right. So I know now when this packet ICMP packet comes back with me, it's encapsulated in an IP packet. Okay. And then the source IP of that IP will be this router's IP. So when it comes back to me, looking at the source IP, I know what is the first router on the path to this. Are you with me? Yes, no, please. How I got the first router IP? Yes or no?
Yes, sir.
Okay. Now you get the idea. Now I'll set bit TTL equal to 2. Then this will drop it. And then this will come back to ICMP. I'll look at the source IP. I'll get the second router. TTL equal to 3 and so on. And when it reaches the destination finally, it won't come back. It will be delivered there. Okay, now the higher layers may not do anything with it. Okay. But I will not get back anything. If TCP drops it, it won't send an IP. I said, okay. I can do, we'll see when we do TCP, I can do some tricks, but now right now just think that it just doesn't come. So I send 3 packets, 4 packets, 5 packets, doesn't come back. I assume it has reached the destination, which means the last one that I've got is the last router on the path. Okay. So think about it. Okay. But why is it not foolproof? Okay. Why will it not always give me the route? It should, right? It will not, because for a simple reason, 2 reasons. Okay. One simple reason that ICMP packets may get lost also. And my internal, the IP packet that is traversing may also get lost. The router may never receive. Now that one we circumvent by sending multiple samples rather than just single one. That too with same with ping and bar. Okay. The other reason may be that, remember, this is a datagram approach, which means the route is not fixed always. So the first packet that goes when you are doing TTL equal to 1, 2, 3, this went through here. Now when you send for the TTL equal to 4, the path may have changed through here. Okay, so there may be some other router. So you think this is the 4th router on the path, but this is actually not the 4th router. So this path may have changed this. Because the routes may change also in between, because you are sending multiple packets over time and waiting for the responses. Within that time, the path that is being followed may change. So you may not get the exact route. But this is a good way of knowing, typically, like how many hops you have, and kind of standard this thing. So ping and trace route, and therefore echo request and echo reply and time exceeded, I want you to remember pretty well. Okay, I don't want to remember exact values like 11 and all those things. Okay, what do they do? I want you to remember. Okay. And this is for any other error that is caused the packet to something, somehow the packet got corrupted. This one also has a very specific need. So I've just listed all of them. You may just look at them. The ones that I'm really interested in are the 3 things. Okay, echo request reply and timestamp receipt. Those are the ones that you should know very well. Okay, and this destination unreachable also you should know, because it relates with things that you have seen, like looking up routing tables, sending ERP requests, and so on and so forth. Okay, so I may give a question like this. For example, I may give a question basically saying that, suppose the network find, as a routing table entry and then sends an ARP request and nobody responds. What will happen? Now, if you don't remember this ICMP, you will just say the packet will be dropped. But the answer that I'm expecting is the packet will be dropped and an ICMP reply will be sent to the thing with the destination unreachable. I don't want to know the codes or the exact thing, etc. Okay. So you need to know exactly when some event happens, what all sub events are triggered. So that's how you piece together the different protocols, rather than just looking at when you study one protocol and you say, oh, this happens, then that happens. But lots of other things happens. Okay, and this one is another thing maybe. This again, these are not very huge. Okay. I just listed them for your reference, but the two that we are most interested in again is echo request reply, time exceeded, and somewhat destination unreachable. Okay. So we have covered mostly IP, but then there is a very practical problem that we see that will do. That's the last thing we'll do in IP. I'll just introduce the problem because we're a little bit out of time, and then we will come back and talk about it, start with it tomorrow. So this is called network address translation. Actually, let's start with it tomorrow. I think 11:52, there is not much point starting with a new topic. But we'll do it quite quickly tomorrow because we want to start with TCP and make some progress tomorrow. So what you have done so far is looked at IP header, IP forwarding, fragmentation reassembly, and details of ICMP, as I said. Part of that you should remember. Try, see, I explained ping and trace route to you. Okay? Try thinking that if you had to write a ping tool, if you have to write a trace route, okay, what is it that you need to do? Don't worry about what is available to you. What is it that you need to do? Actually, the next assignment, I'm not sure, okay, but what my plan was to ask you to write a simple ping tool. But then that will require you to learn something called raw sockets, and the way some of you are cribbing basically not being the class about load. I'm not sure whether I want to do that. Yeah, we may give you something simple. Yeah, I think that you have known already. But then that's, raw socket is very, very interesting. So it allows me to actually manipulate headers. But again, just think, as I said, just think that if you have to do a ping tool, you have to do a trace route tool, what do you need to do? Just as if you are writing the code. I don't want exact calls or anything, any language specific calls or anything like that. And the other thing that I said, I'm telling it again and again because it's extremely important for learning, is you learn the basics, but then you always try to apply in systems. And in this course, you always try to think basically that as a packet moves along the layers, what happens to that packet? You're learning different headers and so on. Just think every header field, how will it be processed? The software will look at it. What will it do with every header field? Or if it's coming from above, basically, what values will you put in those header fields? Okay. And how will this thing behave? So you have these acts and all these things. We'll look at TCP things, will get more complicated. But I just give you an example. Okay. You can think about if you don't find the host address, what do? You can just say that, okay, packet is dropped. But that's just one part of the story. Okay. Think about the entire thing is what is happening. On this port address I pointed out. In the destination unreachable, ICMP, there is something that says port unreachable. Now ICMP is actually is an IP packet. So what it has is an IP header, ICMP header, and ICMP data. Where is the port in that? Okay. When the IP packet got dropped, okay, where is the port in that? So to do that, basically, something has to happen. Either TCP will have to tell IP again that I cannot deliver to the port, send an ICMP, or IP have to look at the protocol field to see it is TCP. Therefore, let me look at the TCP header. I'm not telling what is happening, but all I want you to get this question as to how can ICMP know that port is unreachable? When an IP packet is dropped, how can we know that the port is unreachable? So that when we send the ICMP packet, we can set that port field. The type field is destination unreachable, port field is port unreachable. When you do things like this, you get the questions, you get, the interlinking within the protocols. So we're out of time. I'll end with that. We're almost done with IP, except for something very practical that you also see. So that I'll do tomorrow. We'll go for TCP. So tomorrow we'll kind of start by 8:10. We'll positively start. So be on time. Whatever few numbers are coming in class. Okay, class is dismissed. If you have any questions, I'm still here.